This lecture is about the electric potential energy, meaning the potential energy associated to what turns out to be a conservative force, the Coulomb force. And before you see this lecture, you should probably review the concepts of work, potential energy, energy conservation, either in the previous video or in lecture notes from the first semester course from mechanics. At the beginning of this video, I'll give a very short reminder of some of those topics, particularly how we calculate work and the different ways that we can calculate work. And then I'll do a derivation of the potential energy associated to a pair of charges, meaning the potential energy that comes from the Coulomb force acting on one of those charges. And finally, we'll do an example where we use that potential energy function and also apply it to energy conservation. Next time we'll talk about something new, something that doesn't have an analog in mechanics, or at least not one that you usually talk about in Physics 230 or 220. It's called the electric potential, and it basically there's an analogy between the electric potential energy to the force as the electric potential is to the field. So it's basically just a potential for the electric field itself. So just a quick review about the topics of energy. Again, you should take a look at the previous lecture video, the review of work and energy, if you want to see all the details of this. But all of energy comes about from the definition of work. So we make a definition which is the work done by a constant force over a straight line path delta r, and we write that work as the work done by the force, and sometimes we put the path explicitly there as well, and that's equal to the force dotted together with the displacement vector. And that's just a scalar product, so you could also write that as magnitude of the force, magnitude of the displacement, cosine of the angle between the force and the displacement. And this sort of typical example of dragging a box across the ground, you have a force which might be at some angle with respect to the ground, and you have a displacement which is just the vector of its change in position over some path. So the path is the displacement vector here, and the force is pointed in some direction with respect to that, and then you can calculate the work done in this way. So that's just a definition. It's a way that we can take something in the realm of forces and get back something in the realm of energy. So everything that we talk about that has to do with energy comes from that little definition. Now the first thing that you need to do is you need to expand that definition. It's obviously a very special case to talk about a constant force, a force that doesn't change over the path, and a straight line path. We'll try and deal with more general paths and more general forces. So what do you do if you don't have a constant force? If, for example, you have a force that changes over time, well, then you have to break up the path into segments. And so one example of that is the mass on a spring, where we associate a position of that mass in terms of its distance from the equilibrium position where the spring is unstretched. And if you wanted to go from one point to another, I don't know, from here to here, then the force is actually changing as you go along that path. So there's a spring force. The spring force looks like this, but its x component depends on the value of x. So as you get further and further out, the force has a greater magnitude. It always points backwards. That's what the minus sign gives you. So this is a changing force over a straight line path, and we'll always call that straight line path the x-axis, whether it's for a spring or anything else. And you can start to see how you might do this. You just try and create a Riemann sum. So you chop this thing up into little delta x segments, and then you look at the force over each of the segments, and you assume that it's constant. And if it's constant over those segments, then you can use this expression up here to figure out what the work is. So the total work then would be the sum of the work on each of the paths. Let's call it n. So for n goes from 1 to capital N. And that would be the sum of the force at each of those positions, dotted together with the displacement, which in this case is just delta x. And then that will become an integral. Let's write it on the next line. Which is the work over a straight line path done by a force is equal to the integral, where x goes from x initial to x final of the force, of the vector, but the force, the x component of the force as a function of x dx. So I can actually make one quick change to this, which is to say that if it is a long straight path, then the displacement always points along the x-axis, and therefore you only get one component to that dot product, which is just the sum fx of x sub n delta x. So in this dot product here, delta r always points along the x-axis, and therefore you just get back the x components. So you can see why this becomes this integral here. And if you go back and look at some of the previous lecture notes, you can look at the exact proof of this expression. But we're going to use this expression quite a bit. It's the work done by a potentially changing force, but over a straight line segment. Okay, now what if you have an arbitrary path? So you could have, for example, a person that's riding a bike on a curved path, and you might be interested in what the work done by the normal force is. Well, the expression, which I won't prove, but it's basically found by doing exactly the same thing except using a generic delta r segmenting the path, is if you have a path, and let's just draw that path here, like this. We usually write it as a C, it's a curve. Then the work done by the force along the curve is equal to the integral over the curve of f dot dr. And that really just means the integral of the force dotted together with the velocity vector integrated over time from some initial moment to some final moment that specify the initial and final positions on that curve. So this is the generic expression for how to find the work, and we won't really use it very often, except to look, for example, at f dot v and see that it's 0. So one example is the one that I've drawn over on the left here, which is that as the bike travels along the curve, the velocity points along the curve, but the normal force points perpendicular to the curve, and therefore the work done by the normal force will turn out to be 0 at each little segment. So this is the generic expression for work done by a force. It, of course, implies the previous two expressions that we had, which are special cases. One last thing to mention in general about energy is the idea of a conservative force and a potential energy. And the statement is that a force is called conservative if it turns out that the work done between 2 points doesn't depend on the path taken. So you could talk about that in terms of a spring. So we have the spring force. Oops. So you could imagine that you take this object, this mass on the spring, and you want to move it from some initial point, point A, to some final point, point B. And it turns out that if you calculate the work done by the spring force in this path, where you just go straight from A to B, that the value of the work would be exactly the same as if you went on this path, where you pulled it out first and then went all the way back to B, or if you went past B and then came back, or if you went this way and then came back and then went that way. Every single path will give you exactly the same work, because as you go outwards, the spring force pointing backwards gives you negative work, but as you come inwards, the spring force pointing inwards along the displacement gives you positive work, and they'll exactly cancel out for some path like that. So that's one example of a conservative force. Another is the force of gravity, and also we'll see in a second the force of one charge on another charge. So if you have a conservative force, then you can define something called the potential energy, and the potential energy is just the potential energy between 2 points. So we could talk about the potential energy of the mass on the spring at point A with respect to point B, and that value, the change in potential energy from A to B, is just minus the work done that it takes to go from A to B. And what I mean by RA and RB is that you could simply have a coordinate system like this, and you could give the positions, the initial and the final positions, as RA and RB. And in a more complicated example, you could have some mass, big M, and some little mass, little m, which you want to move from one point in space to another, say from RA to RB. So the potential energy difference between those 2 points in space is the opposite of the work done to go between those 2 points in space. And you notice we don't mention the curve taken, because from the definition of a conservative force, it doesn't matter which curve you take. You can take any curve you want. You can go straight across here, or over here, or wherever you want. And then if we define conservative forces, then we can have this idea of mechanical energy conservation, which is if we only have forces that are conservative acting, then the potential energy plus the kinetic energy initial is equal to the potential plus kinetic final, where the kinetic energy is defined from something called the work energy theorem to be 1/2 mv squared. And you can see why all of that's true if you take a look at the previous lecture video and previous notes from last semester. So let's apply this to determine the potential energy for a pair of charges. And what we mean by that is a potential energy associated to the Coulomb force. It turns out that that force, which you know looks a lot like the gravitational force, is also a conservative force, just like gravity. Coulomb force, remember, is FQQ is equal to K, absolute value Q, absolute value big Q, over R squared, which of course looks just like the gravitational force with sort of a change in constants and replacing charges with mass. So it's not surprising that they would be similar in that way. And we're going to go through the derivation of the associated potential energy in exactly the same way that we went through the derivation of potential energy for the between two masses. So let's do it. So start by writing the definition. And that is the potential energy associated to the Coulomb force. The difference in that, as going from one position to another, is equal to minus the work done by that force in going from one position to another. So what do we mean by that? Well, we could have one charge, call it big Q, and another charge, call it little q, and we could move little q from one position in space to another position in space. So we could call this point A and call this point B. And in fact, we could put a coordinate system at the center and call this position RA and position RB. And now we need to find the work between those 2 points. Now remember, because it's a conservative force, we can use any path that we want from A to B, and we'll get the same answer. So in these problems, you want to choose the path carefully so that you can calculate the work easily. And what it turns out is the easiest thing to do is to assume that B lies on a circle of a radius RB about the source charge, and then take your path going straight away from the source charge, and then traveling along that circle for the second part of the path. So we have, we could call this like path 2 and path 1 here. So if this is our expression for the potential energy, then we see that we can break it up into 2 parts, and that is the work done along path 1 from, well, it's exactly along path 1, it's not from A to B, plus the work done along path 2. And now we have a work that we need to calculate, so we need to decide which expression for the work we can use. And if we look at the first one, we see that we've chosen a path which is straight. Now, along that path, the force might be changing. In fact, it is changing, because the force that we're talking about, and let's just draw it here, the force that we're talking about is the Coulomb force. So if these happen to be both positive charges, then that force will point directly away. It's a repulsive force in that case. So this is FQQ. And the magnitude of that force is changing because we see that the magnitude changes as the distance between the 2 charges changes. So what we do is we use our example for a straight line calculation of work, and to do that we assume that this is the x-axis. Remember, you choose the straight line to be the x-axis, and then we're going to go from one point in the x-axis, which we could call x initial, to another point in the x-axis, which we can call x final, and we just write down the expression that we have for the work done by a changing force over the x-axis, which is from x initial to x final, the force, the x component of the force, as a function of x dx. Then we have the second curve, part of the curve, and that is along this circle. And if we draw the force at that point, so here's potentially a place where the second charge will be, and then the force is going to be pointed like this. Well, you see that the force is perpendicular to the velocity vector of the curve as it's being brought along that path. So that means that we can use that really complicated expression, the force dotted with the velocity, integrated over time from some initial time to some final time. But we don't need to think about that at all because the whole thing just goes to 0, because the force dotted with the velocity is equal to 0. Another way that you can think about that is the integral of f dot dr is equal to 0. So the dot product of the force and the dr vector is equal to 0. Although it's not exactly clear what we mean by dr. It's really just symbolic notation. So it might be easier to think about it in terms of the force multiplied by its velocity, the tangent to the curve. So you can see we've simplified the problem now. Because of our choice of paths, we really only need to calculate the work going from here to here, and that's a straight line path, and so we just need to calculate this integral. So what we find is the x initial, well, that value is just the magnitude of RA, and then x final is the radius of the circle, which is the magnitude RB. The force we have up here, but now we need to write it in terms of this x. So what's the x component of this vector right here? Well, we see that it's positive, if we assume that q and q are both positive. And we see that the distance from the center, which we call r in this equation, can also just be thought of as the x value along that axis. So I can write this in terms of x as k qq over x squared dx. And we might look at that for a second and see if it also holds if q and q are, for example, positive and negative. So if that were the case, then one of these would be positive, one would be negative, and the whole thing would be negative. The force would be attractive, and that would mean that FQQ should have a negative x component, and that would work because I would have a minus sign in here because of the signs of the charges. If they're both negative charges, then that should be a repulsive force, but the two minuses cancel out to make the x component of the force positive, and so it still works. So this works for any value of the charges that we want. Okay, now we can calculate. So we have minus kqq, we have minus kqq here, and then we have the integral from RA to RB of x squared, but that's just going to be minus x to the minus 1 from RA to RB. The minuses cancel out, and you get kqq times 1 over RB minus 1 over RA. So that is the expression for the potential energy difference between point A and point B. Now, if you remember from the review of calculating potential energy, we're often interested in finding the potential energy function, which is just U of R. And we do that by choosing a place where the potential energy is equal to 0. So let's write that out explicitly. So let's say, so assume or choose that the potential energy when the separation of the charges is infinity is equal to 0. So if you take these two charges and separate them completely, then we'll assume that that spot, the potential energy, is equal to 0. So now we can say, okay, I'm going to write down my expression, which is delta U is equal to the thing that we have up there. So it's U of RB minus U of RA, final minus initial, is equal to KQQ of 1 over RB minus 1 over RA. And then I'm going to use the information, use the choice that I made by assuming that, for example, I start out at infinity, so let's let RA equal to infinity, and I end up at some just sort of random position R. So if I plug that in, I get U of RB is R, U of R minus U of infinity is equal to KQQ times 1 over RB is R minus 1 over infinity. Oops. And what do I find? Well, I get u of r, because we assumed that u of infinity was equal to 0, is equal to kqq over r, because, of course, 1 over infinity is equal to 0. That's just arithmetic. So we find final expression, the potential energy associated to a pair of point charges is kqq over r. Now let's apply it. So we'll use that potential energy function to do some problem. So the problem is that we have a square. Let's draw a square. And we have charges at the points of that square, at the vertices of that square, corners of that square. And they're each of charge q and mass m. We can think about them as being all positive charges, for example. So we have q, 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 q. And we're told that the square has length L. And we're asked two questions. The first question is, what is the potential energy? Call that part A. Of the 4 identical charges held at the corners of the square. So something is holding them there. They're positive charges, so they would experience repulsive forces, but there must be something holding them there. And we're asked, what is the potential energy? So we'll use our potential energy expression, this thing here, and we might rewrite this up here as uqq of r, just to say that this is the potential energy associated to a pair of charges. So you see that potential energy comes from the pair of charges, not just from a single charge. So that means that the total potential energy here, U total, is going to be the sum over all pairs of U, Q, Q, just in symbolic notation. So that means that I have to look at, for example, this pair, and 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 this pair. And I have to write down an expression for each of those pairs. That will be the total potential energy. Let's get rid of all that stuff. So the total potential energy is going to be, well, I have this pair first, and so that is, looking at my equation, K Q squared over R, which is L. But notice I have 1, 2, 3, 4 of those. So I can just write, I'm going to get rid of those circles first. Hi. So I can just write 4 of those things. How many more pairs do I have? Well, now I have some diagonal pairs. So I have 1, 2 diagonal pairs. So I have 2 times K Q squared over, and then I need to know the length of this diagonal, but you can see based on this triangle here that we have D squared is equal to L squared plus L squared, or D is equal to the square root of 2L squared, so that's the square root of 2L. So this thing becomes square root of 2L in the denominator. And that is the total energy associated to this collection of charges. Now part B, it says if one charge is released, how fast will it be traveling when very far away? So you take one of these charges and you detach it from the wall, however it was fixed there, and you let it go. And of course, because it's going to experience repulsive forces from these other charges, it will start to go away. So the question is, how fast will it go? Well, it'll go at a different speed now than when it's going later, but eventually it won't feel any more force, and so it'll settle down to a single speed, which will have as it gets to infinity. So how do we answer this question? Well, we use conservation of energy. So mechanical energy initial is equal to mechanical energy final. That is the initial potential energy plus the initial kinetic energy is equal to the final potential plus the final kinetic energy. Oops. And we'll take our initial condition to be just what you see in the picture, and our final, so final is going to be, you have these charges still here, but then way off in the distance, you have that third charge, and it's moving with some v final away. So that's our final case. So let's just try and write these things down. We already figured out the initial u value. That was from part A. So we can just write 4kq squared over L here, plus 2kq squared over square root of 2L. That's my initial potential energy. My initial kinetic energy, well, they're all just sitting there. Nothing is moving. So all of my 1/2 mv squareds are equal to 0. So that will just be 0. And then my final, well, it's going to look, we know that the kinetic is easy to write down. That one's going to be 1/2 mv final squared for a single charge. That's the only one that's moving, so we only have one kinetic energy term there. And then the potential energy term will look similar, but I've lost some of my pairs. So let's just count what we have. So I still have one diagonal pair instead of two, and I have 1, 2 pairs side by side. And that's it. So instead of my initial expression, I now have 2kq squared over L plus 1kq squared over square root of 2L. And if I do some algebra, I get 1/2 mv final squared, and then I'm going to get, well, 4 minus 2, so that's 2kq squared over L, and 2 minus 1, kq squared over square root of 2L. And then you can just solve. So v final is going to be equal to 2 over m times that whole thing, 2kq squared over L plus kq squared over square root of 2L, and all square rooted. I think that's the answer.